By the way, this happens in high school algebra again, if you want to see the analogy. Look at, for example, the algebraic equation a plus b squared. We learn in algebra that this is a squared plus 2ab plus b squared. Observe that we do not need to have a picture to understand how this works. Oh, to be sure, if we had a picture, we get a tremendous amount of insight as to what's happening here. Namely, let's visualize a square whose side is a plus b. On the one hand, you see, the area of the square would be a plus b squared, you see, the side squared. On the other hand, if we now subdivide this figure this way, we see that that same square is made up of 4 pieces, having 1 piece of area a squared, 2 pieces of area ab, and 1 piece of area b squared. And so we see, on the other hand, that the area of the square is a squared plus 2ab plus b squared. And so again, observe that whereas this stands on its own 2 legs, the picture helps us quite a bit. By the way, we could continue this with a cube over here. Namely, it turns out that a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And again, if we wanted to, and we won't take the time here, but if we wanted to, we could now draw a cube whose side is a plus b. Namely, we could take the same diagram that we had before and now make a 3rd dimension to it. And if you did that, you would see what? That the cube, whose volume is a plus b cubed, is divided into 8 pieces. 1 of size a by a by a, 3 of size a by a by b, 3 of size a by b, and 1 of size b by b by b. Again, the picture is a tremendous visual aid. Now, the key step is this. If we were to now give in to our geometric intuition and say, look at, why worry about algebra when it's so much easier to do this thing by geometry? The counterexample is, consider a plus b to the 4th power. Now, by the binomial theorem, and I might add, the same binomial theorem that allowed us to get these results, we can also write that this is what? It's a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Now, it's not important how we get this result. The important point is that analytically, we can raise a number to the 4th power just as easily as we can to the 3rd power or the 2nd power. The only difference is that in the case of the 2nd, the 3rd power, we had a picture that we could use. In the 4th power case, we didn't have a picture. And what a tragedy it would have been to say, hey, we can't solve this problem because we can't draw the picture. And by the way, as a rather interesting aside, notice the geometric influence on how we read this. This is called a plus b to the 4th power. But somehow or other, we don't call this one a plus b to the 3rd power. We call it a plus b cubed, suggesting the geometric configuration of the cube. And here we don't usually say a plus b to the 2nd power. We say a plus b squared. You see, the idea is that when the picture is available, it gives us a tremendous insight as to what can be done, and it helps us learn to visualize what's happening analytically. In fact, what usually happens is we use the picture to justify what's happening analytically when we can see the picture, and then just carry the analytic part through unimpeded in the case where we can't draw the picture.